Hello and welcome to a new video. My name is Herwig Juster, and today we discuss the difference between design properties and inherent properties of thermoplastics. Okay, let us get started. First, let's have a look at the relationship of properties and geometry. And here as an example, I've selected a simple beam design element. So the beam is fixed here on a wall and we have a certain force P, which leads to a deflection of the beam, which is then here the delta. So delta is the load times 4 times the length of the beam, and divided by the modulus of elasticity, and then we have the width and the thickness of the beam. And there you see a nice combination of geometry and material properties. So the modulus of elasticity is a material property which can be measured, which is then plugged into this equation. And here in the normal use case, it's always use the value at room temperature. However, when your application has a continuous use temperature of 80 degrees C, you have to put in here another value to already correctly predict the deformation. And this is already one of the key points here, relationship of properties and geometry. And the success key, you can say, is that the property knowledge of material at application conditions. And with this know-how you can make improved design decisions. And always keep in mind this example with the beam design and the modulus of elasticity, room temperature, and then at the application condition to check them both. Okay, so what are design properties? Design properties are, for example, stiffness and strength. You can have your design made in a way that it is stiff. You can add ribs, you can add a certain wall thickness variation, and improve the material. It doesn't matter if it is amorphous or semi-crystalline thermoplastic. You have stress crack resistance, so you can really design in a way that stress cracks can be minimized. Impact resistant, also certain designs allow for a better impact resistance. The same with creep resistance. So to make the wall thickness and the angles of the part in a certain way to make creeping a minimum. And also flammability. So with the thickness of the wall thickness of the part, you can influence the flammability level to reach V0, V1, different millimeters. Although the material is not inherently flame resistant, however, you can, with the certain wall thickness, you can reach a certain V0 level then. And also the same with fatigue resistance. So these are the some examples of design properties which we can actively influence. Then on the other hand, we have the inherent material properties. So inherent material properties are all thermal transitions. So glass transition temperature, crystallization temperatures, the melting points, they are really characteristic to the material itself. And this is not changed by the design of the part. It is always there. The same as with the chemical resistance. And for example, we have before heard stress crack resistance, and here when the material has a bad chemical resistance, it can then also trigger the stress crack. So this is called environmental stress cracking. So one lead then can lead to the other. So you can have a proper design, however, when the chemical resistance is not enough, then you still end up in stress cracking situations. Oxidative stability, also when you think of polyolefins, here we need stabilization, otherwise the design will not prevent that the UV light will destroy, for example, the polymer chains, and with then when you have a sheet for a glass house, for example, will be broken. Similar to oxidative stability is the wear resistance. So here is also an inherent property that, for example, semi-crystalline thermoplastic behave here better in wear, in terms of wear resistance, than amorphous. And it's also only so much you can do then with the design, and here the material is not proper chosen. The best design is also not helping them. Okay, to sum up, we have currently an explosion of also of information plastics data, so plastic data sheet, long-term, short-term, etc. So to tackle this and to not get lost in the labyrinth, I would say it's important to focus on the fundamentals, understanding the material properties and the design requirements, and then combine both inherent properties with the design properties to get the optimal material part solution. And so with this understanding you can really build up to a commercial solution for any application. So it's really, when you start from this, it improves the all over application design phase. However, without this stable starting point, it's, as I previously said, you get lost in the labyrinth of trade names and material property snapshots, and you run into the situation that you have to cross your fingers and hope when the first part gets out of the injection molding machine that everything goes well. But we don't want that. We want really to actively steer good solution from the beginning of our material selection journey. Okay, if you want to learn more on polymer engineering topics, I highly recommend my blog, findoutaboutplastics.com, as well as my online courses on material selection. I will link you both the blog and the online courses in the description below. Okay, which video to watch next? In this video we discuss 6 important areas for polymeric materials in electric vehicles, so check it out. I'd like to thank you for watching, and do not forget to subscribe and smash that like button. Till next time, bye!